All right, so let's do a couple of examples. These again are exercises out of your textbook from section 3.6. So the first one we have here is to find the derivative of the inverse tan of x squared. So I'm just going to rewrite for a second that the derivative of inverse tan of x is 1 over 1 plus x squared. Now here I have the inverse tan of a function of x. So I actually have to use the chain rule on this, and I'm going to just use this box method. So when what I have in the argument of the inverse tan function, or what I'm taking the derivative of, is not just the inverse tan of x, but the inverse tan of something more than x, a function of x, then that derivative using the chain rule is going to be 1 plus whatever that argument is squared, using the basic rule, but then I have to times by the derivative of whatever that argument function is with respect to x. Or maybe you like this notation a little bit better, hang on, times the derivative with respect to x of whatever that argument is. Okay, so look at the similarity for the general rule for the derivative of inverse tan of x and what I have written here, where what I'm taking the inverse tan of is not just x, but a function of x. So to take, let me use my red here, to take the derivative of the inverse tan of x squared, I have to do 1 over 1 plus x squared squared times the derivative of x squared with respect to x. Okay, so y prime, or dy dx, is 1 over 1 plus x to the fourth, that's x squared squared, times the derivative of x squared, which is 2x, and often the way we write this is 2x over 1 plus x to the fourth. Now make sure that you realize you cannot simplify. You cannot break that fraction up into 2x over 1 plus 2x over x to the fourth. That's bad algebra. All right, let's look at number 20. Find the derivative of this cap f of theta, that is the arc sine of the square root of the sine function. Okay, so again, let's look at our general rule for the derivative of the inverse sine of x. That's what we just derived in the previous video. That's 1 over the square root of 1 minus x squared. Now when I'm finding the derivative of the arc sine of something other than plain x, I have to use the chain rule. So the derivative of the arc sine or inverse sine of something that's not just x is 1 over the square root of 1 minus whatever that argument is squared. Then I have to multiply by the derivative. In this case, we'll be working with theta, but whatever that argument function is. Okay, so I'm going to actually, instead of filling in the boxes, I'm going to write all this out. So again, notice my input variable is theta, not x, so I was just doing something more general there, but I have to take 1 over the square root of 1 minus the square root of sine theta squared times the derivative with respect to theta of the square root of sine theta. Now this is a double whammy because let's just take a sidebar here. Maybe I should call it sidebar. The square root of sine theta, that is sine theta to the 1/2. The derivative with respect to theta of that, I got to bring my power 1/2 down. I got to raise sine theta to 1 lower power, and then I have to times that by the derivative of sine theta, which is cos theta. Okay, so back to what I was working on here. Cap f prime, that's 1 over the square root of 1 minus, now the square root of sine theta squared is just sine theta. Then I have to multiply by the derivative of the square root of sine theta, which I just took off in my sidebar. That is 1/2 times sine theta to the negative 1/2 times the cosine of theta. Now again, should you simplify this? Well, I don't know about should. It would be nice if you understood how to do it. One way we could simplify it is with a cosine theta in the numerator, and in the denominator we have a 2. We have a square root of sine theta. That came from raising sine theta to the negative 1/2 power, and then we also have a square root of 1 minus sine theta. So again, is it crucial, necessary that you simplify? No. Would it be good if you understood how the simplification works? Absolutely.